let's see the behavior of passive circuit elements. So first of all, behavior of resistor R. For a resistor, current and voltages are related like this. V is equal to I into R. The current through a resistor will change instantaneously if voltage changes instantaneously. Similarly, the voltage will change instantaneously if the current changes instantaneously. Let's consider this circuit. At t is equal to 0, resistor is energized by means of this voltage source. So just before switching at t is equal to 0 minus, current through the resistor was 0. So immediately after switching, current through the resistor is changed to V by R. So the current and voltage in resistor will change instantaneously with instantaneous change in voltage or current. The resistance value is not changing with respect to time. Therefore, resistance is a static device. Next one is behavior of inductor L. For an inductor, current and voltage is related by this equation. VL is equal to L into di by dt. Voltage across the inductor is proportional to rate of change of current. So it is to be noted that it is impossible to change the current through an inductor by a finite amount in zero time. So this requires an infinite voltage across the inductor. So it is practically not possible. So let's consider a circuit like this. Here at t is equal to 0, this inductor is energized with a DC voltage source. So at t is equal to 0 minus, that is just before switching, the current through the inductor is IL0 minus is 0. There is no initial current. Then at t is equal to 0 plus, that is immediately after switching, inductor current, that is IL plus, become 1 by L integral 0 to t Vt dt. If some initial current is there, that is IL0 minus is equal to I0, some initial current, then we can write IL0 plus is equal to 1 by L integral 0 to t Vt dt plus I0. So at t is equal to 0 plus, that is immediately after switching, the inductor voltage become L into di by dt. So as I mentioned earlier, dt is very small, 0 time. So under that condition, what is VL? If this is 0, this entire part become infinity. So under that condition, VL become infinity. It is practically not possible. So as I mentioned earlier, it is impossible to change current through inductor by a finite amount in 0 time. In order to obtain that one, VL should be infinity within 0 time. That is practically not possible. So that means current through the inductor not changes instantaneously. That means an inductor does not allow an abrupt change in current through it. In this case, when we are considering initial current as 0, immediately after switching is also IL 0 plus, that is 0. If you are considering initial current, say I0 before switching, so IL 0 minus is I0, and immediately after switching also the current through the inductor become I0. Now let's consider another circuit. Assume initially the switch was in position 1. That is at t is equal to 0 minus, that is just before switching, current through the inductor is I0. Why? Because the circuit was in closed condition. Say this current is I0. So initial current is I0, that is the condition just before switching. Now we are going to change the switch position from 1 to 2. Under that condition, so immediately after switching, that is t is equal to 0 plus also, current through the inductor remains I0. So we know the inductor voltage during switching, during the transient period, is L into di by dt. So as t tends to 0 during immediately after switching, VL become infinity. VL become infinity means it is open circuit. So immediately after switching, Inductor is open circuit. Now let's see the behavior of this inductor as t tends to infinity. As dt denominator become infinity, this entire term becomes 0. So what is the meaning of VL becomes 0? When voltage across a particular element becomes 0? When it becomes short circuited. So corresponding to T0 plus, inductor act as open circuit. Why? Because VL is infinite. And corresponding to T tends to infinity, steady state condition, inductor act as short circuit. So this is one of the important concept in DC system. That is, if the system is working under steady state condition, in DC network, inductor act as short circuit. Now let's conclude the conditions which we got in inductor case by means of this table. So this is case 1, that is initial conditions of the system. Initially the current through the inductor may 0 or it is having some value I0. So corresponding to no initial current. So immediately after switching, that is t is equal to 0 plus VL is equal to L into di by dt, dt tend to 0, therefore VL become infinite. So corresponding equivalent circuit is open circuit. At t tends to infinity, corresponding to steady state, VL is equal to L into di by dt, dt become infinity, therefore VL becomes 0. So VL becomes 0 means short circuit. Now let's consider the second case, that is initially some current I0 is flowing through inductor. So just before switching, current through the inductor is I0. Under this case, whenever the switch is getting closed, immediately after switch is getting closed, that is at t is equal to 0 plus, the corresponding equivalent circuit is like this, is represented by a current source. So that current source value is initial current I0. Corresponding to t tends to infinity, that is steady state condition, this is the equivalent circuit. The VL is equal to L into di by dt, dt tends to infinity, therefore VL becomes 0. So corresponding to that condition, some short circuit will come like this. Next case is behavior of the capacitor. In the case of capacitor, we can have this relation Q is equal to CV. From that we can find the voltage and current relationship like this, IC is equal to C into dV by dt. So from this relation it is clear that current is directly proportional to rate of change of voltage dV by dt. So from this it is clear that it is impossible to change the voltage across the capacitor by a finite amount in 0 time. So let's consider this circuit for that one. So t is equal to 0 minus, that is just before switching, the capacitor voltage is assumed to be 0 volt. Immediately after switching, that is t is equal to 0 plus, the voltage across the capacitor become V. So within 0 time, it is not possible to change this much change in voltage across the capacitor. So at t tends to 0, I0 plus become infinity. Why? Because when we are substituting 0 here, IC become infinity. That is short circuit. As the current is infinite means that corresponding equivalent circuit is short circuit. So it is impossible to change the voltage across the capacitor by a finite amount in 0 time. In order to achieve that one, current through the inductor become infinite. A capacitor does not allow an abrupt change in voltage across it. That is, the capacitor's voltage just before switching is equal to just after switching. Vc0 minus is equal to Vc0 plus. So from that earlier relation, I is equal to C into dVc by dt, we can find this relation Vc t is equal to 1 by C integral 0 to t I dt plus initial voltage, where V0 is the initial capacitor voltage. Now let's consider the second case. Here, initially assume the switch was in position 1. Under that condition, voltage across the capacitor is V. Let it be V0, denoted by initial capacitor voltage. So just before switching, at t is equal to 0 minus, Vc0 is equal to V0 when the switch was in position 1. Now what happens? switch is placed in position 2 at t is equal to 0. So immediately after switching, that is t is equal to 0 plus, the capacitor voltage doesn't changes. Capacitor opposes an abrupt change in voltage across it that we discussed earlier. So due to that property, V00 plus, that is VC00 plus, immediately after switching, the capacitor voltage is retained as V0. The switch is in position 2. So during transient, we can have a closed circuit like this. A current will flow through the circuit. So during transient, this acts as source. So we can have this voltage and current relations as we discussed earlier. I is equal to C dVc by dt. Immediately after switching, as dt tends to 0, I become infinite, that is short circuit. Corresponding equivalent circuit is short circuit. As t tends to infinity, that is corresponding to steady state, this is infinity, therefore I is 0. Corresponding equivalent circuit is open circuit. Now let's see what is the conclusion which we got in this discussion. So corresponding to initial condition, the capacitor may or may not have initial voltage. So in first case, let's consider there is no initial voltage across the capacitor. As the current relation is I is equal to C into dVc by dt, at t is equal to 0 plus immediately after switching, dt is 0, therefore I is infinite. As I is infinite, corresponding equivalent circuit is short circuit. As t tend to infinity, I is 0, so it is equivalent circuit. Now let's consider initial capacitor voltage V0. When the switch is just closed, this voltage source acts as one of the source for delivering current through the circuit. Corresponding to t tends to infinity, I becomes 0. So under that condition, this is the equivalent circuit. This is the final summary. As it is clear from here, the resistance value is constant. It doesn't depend on time. Corresponding to inductor, if there is no initial current, corresponding to T0 plus, it is open circuit. Corresponding to T infinity, it is short circuit. Similarly for the capacitor, if there is no initial condition, for immediately after switching, it is closed, short circuit. For steady state, it is open circuit. Similarly for inductor having initial current, so corresponding to t is equal to 0 plus, this is the equivalent circuit. Corresponding to steady state condition, this is the equivalent circuit. And similarly for capacitor.